Okay, so in this video, I am going to discuss the Pascal's triangle and identities using the concept of combinations. And this video is also a continuation of the discussion on binomial expansion using binomial theorem. So first, we're going to show our expansion of binomial using the binomial theorem. Okay, and then through a Pascal's triangle, of course, and eventually we shall have our binomial coefficients from the binomial expansion in the Pascal's triangle using combinations. Okay, so our topic is all about we have Pascal's triangle and identity. Okay, so first we shall have our Pascal's triangle with the use of the concept of combinations. In our previous discussion, we say that the combination can be evaluated using the formula n CR, or we have the combination of n taken r at a time, which can be solved by n factorial over n minus r factorial in such a way that n is greater than or equal to r. Okay, so using this concept, we shall show our Pascal's triangle through combinations. So we have here 0, 0, that is combination of 0 taken 0 at a time. We also have here our 1, 0, and we have our 1, 1. Next is 2, 0. We have 2, 1, and we have 2, 2. Okay, and the other one is 3, 0. That is combination of 3 taken 0 at a time. 3, 1, combination of 3 taken 1 at a time. We have 3, 2, combination of 3 taken 2 at a time. Combination of 3 taken 3 at a time. Next would be 4, 0. We have 4, 1. We have 4, 2. We have 4, 3. And we have 4, 4. Or combination of 4 taken 4 at a time. And we have here 5, 0. You also have here 5, 1. Just write your combinations in between two other terms above. Okay, so we have here 5, 2. And we have 5, 3. We have 5, 4. And we have 5, 5. The other one, we have 6, 0. We shall try until 10. Okay. We have 6, 1. We have 6, 2. We have 6, 3. And we have 6, 4. Next is 6, 5. Next is 6, 6. Okay. The other one, we have 7, 0. We also have 7, 1, or combination of 7 taken 1 at a time. We have 7, 2. We also have 7, 3. We also have 7, 4, or combination of 7 taken 4 at a time. We have 7, 5. And we have 7, 6. And finally, we have 7, 7, or combination of 7 taken 7 at a time. Next, we have 8, 0. We have 8, 1. We have 8, 2. So again, you must observe that these terms are written in between two terms in the previous row. Okay, in between two terms in the previous row. That's correct. We have 8, 3 here, or combination of 8 taken 3 at a time. We have 8, 4. We have 8, 5. We also have here 8, 6. We also have 8, 7. And finally, we have 8, 8. Okay. Next, second to the last, we have 9, 0 here. We have 9, 1 here. We have 9, 2. Okay. Or the combination of 9 taken 2 at a time. We have 9, 3. We have 9, 4. We have 9, 5. We have 9, 6. We have 9, 7. We have 9, 8. And we have here 9, 9. Okay, last, we have 10 here, 0. We have also 10, 1. We also have 10, 2. We have 10, 3. We have 10, 4. We have 10, 5. We have 10, 6. 10, 7 here. Next is 10, 8. Next is 10, 9. And last, we have 10, 10. Okay, so that is our Pascal's triangle using combinations. So we presented our Pascal's triangle using combinations. Okay, now if we are going to evaluate the combinations, then we have the binomial coefficients. Okay, so again, we present also the binomial coefficients in the form of a triangle, and we call that as Pascal's triangle. So in this case, we have, okay, we have here, so the combination of 0 taken 0 at a time is 0 taken 0 at a time, or combination of 0 taken 0 at a time is 1. Okay, that is 1. And the combination of 1 taken 0 at a time is 1 also. Okay, we have 1, 1 here. And combination of 1 taken 1 at a time is also 1. Combination of 2 here. Okay, let's change our color into black. Okay, so we have 1, 1 here. Okay, the combination of 2 taken 0 at a time is 1. Combination of 2 taken 1 at a time is 2. Combination of 2 taken 2 at a time is 1. Next, combination of 3 taken 0 at a time is 1. Combination of 3 taken 1 at a time is 3. Combination of 3 taken 2 at a time is also 3. And combination of 3 taken 3 at a time is 1. Okay. Another one, we have combination of 4 taken 0 at a time is 1. Combination of 4 taken 1 at a time is 4. Combination of 4 taken 2 at a time is 6. Combination of 4 taken 3 at a time is 4. And combination of 4 taken 4 at a time is 1. Okay, now, what do you observe with the values or coefficients of the binomial in between two other coefficients in the previous rows? For example, what can you say about, okay, what can you say about the sum of 1, 1 here, in which the value here is 2. Sorry. This one. Okay. So what can you say? What is the relationship of 2 here with the coefficients here in the previous row? So if we're going to add these two coefficients, the sum is 2. So we have 1 plus 1 equals 2. What about this one? 3. Okay. So we have 1 plus 2 is 3. 2 plus 1 is also 3. What about here? 1 plus 3 is 4. And 3 plus 3 is 6. And 3 plus 1 is 4. So that the sum, okay, the sum of two consecutive coefficients in a binomial in a Pascal's triangle is equal to the number in between the next row. Okay, in between the next row. So that the Pascal's triangle shows that when two adjacent binomial coefficients in the triangle, say we have 1, 3, are added, the binomial coefficient in the next row between these two coefficients is produced. So we're going to add this in order to produce our second value here. Okay, so 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. So that in the next row, we shall use the same process. We add this one, but of course we have to indicate our first value here. Okay, I'll just change the ink. So we are going to use the same process. We have 1 here. If we're going to add 1 and 4, we have 5. We're going to add 4 and 6 here. We have 10. 6 and 4, we have 10. 4 and 1, we have 5. And we have 1 here. Okay. So these are the coefficients of the binomial when we have x plus y raised to the 5th power. Raised to the 5th power. So we have x plus y raised to the 5th power. Okay, this one is x plus y raised to 0, x plus y raised to 1, x plus y raised to 2, x plus y raised to 3, and x plus y raised to 4. Okay, so our binomial coefficients are 1, 5, 10, 10, 5, 1, 4. A binomial with x plus y raised to 5th power. Okay, so continuing our work here, we have 1 here. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 20 plus 5 is 15. No, sorry. 10 plus 5 is 15. 5 plus 1 is 6. And we have 1 here. Okay, so this is the coefficients of the binomial in the 6th exponent or 6th power. Next is 7. We have 1, 7, 21, 35, 35, 21, 7, and 1. Okay, and we have also 8. We have 1 here. We have 8 here. We have 28 here. We have 56 here. We have 70. We have 56. We have 28. We have 8. And we have 1. So that is our sum, okay, of two adjacent coefficients. We have here 35 plus 21 is 56. 35 plus 35 is 70. 21 plus 35 is 56. 7 plus 21 is 28. And 1 plus 7 is 8. And we have the other one, 1, 9. This is 26. So 28 plus 56 is 84. Okay. Here we have 6, 7 plus 5 is 12, 126. This is 126 also. We have 84 here. We have 36. This must be 36, sorry. We have 9 and we have 1. Okay, and last is we have 1, we have 10, we have 45. Okay, that is 10, that is 45, that is 12, hold on, 10, 112, 120. So we have 10, 11, 12. So we have, okay, 84 plus 126 would be 210 also. Okay, 126 plus 126 is equal to 252. And 126 plus 84 is equal to 210. And we have 84 plus 36 is 120. Okay, and this is 45. And we have 10 here. And eventually we have 1. Okay, so where do we see the Pascal's identity? Where do we see the Pascal's identity here? So let us look at the Pascal's identity using these two different Pascal's triangle, although they have the same values here. Okay, in the Pascal's identity, it says here, let n and k be positive integers with n greater than or equal to k, so that the Pascal's identity could be n plus 1, k here, or the combination of n plus 1 taken k at a time is equal to the combination of n taken k minus 1 plus the combination of n taken k plus 1. So this is our Pascal's identity. Okay, so n plus 1 or combination of n plus 1 taken k at a time is equal to n, or combination of n taken k minus 1 plus the combination of n taken k at a time. Okay, so let us see. Suppose we want our n to be 5. Okay, suppose we want our n to be 5. So we will add our sheet here. Suppose n is equal to 5 and k is equal to 4. Take note that n must be greater than or equal to k. Okay, so here we have n plus 1 is 6. We have 4. Therefore, we have 5 as our n. K minus 1 is 4 minus 1, so we have 3. Okay, plus n is 5, and our k is 4. Okay, so getting the combination of 6 taken 4 at a time, we have 15 equals the combination of 5 taken 3 at a time is 10, plus the combination of 5 taken 4 at a time is 5. Therefore, we have 15 is equal to 15. Okay, so we have our values here. So let us verify. What is the combination of 6 taken 4 at a time? So we have 15. So our values is here, the combination is here. No, sorry, this one. 6 taken 4 at a time. Okay. So we have most likely 1, 2, 3, this one. Our value for the combination of 6 taken 4 at a time, so that the addends or the addends n combination of n taken k at a time is 5. Combination of 5 taken 3 at a time is this one. And the other one is 5, 4. So if we're going to get the combination values of this is equal to the value of 6 taken 4 at a time. Okay, same is true here. If we are going to add, okay, so if we're going to add this one, 10 plus 5, the sum is 15. So that is what we call the Pascal's identity. Okay, the Pascal's identity. Again, may I reiterate that the Pascal's identity shows that when two adjacent, 10 and 5 of binomial coefficients are added, the binomial coefficient in the next row between these two coefficients, okay, is produced. So the two adjacent coefficients are 10 and 5. We add that, then we produce the value that is found in between them in the next row. Okay, so we also have this one, 35, 35. This is also an identity, Pascal's identity. Same here, okay? 8 and 28. It's also a Pascal's identity, okay? So it's so easy to find the Pascal's identity if we have our Pascal's triangle, or if we can solve the coefficients using combination concept, okay? So for the meantime, that ends our discussion on Pascal's identity and triangle. Thank you so much, and I hope you have learned something for the day again.